Okay, hello everyone. My name is Andrew Anctil. This is my project called Class Incremental Learning Acceleration, Harnessing A100 GPUs for Efficient Methods of Experimentation. My advisor for this project was Professor Ming Shao. So I'll give some background on what class incremental learning is. So class incremental learning you can think of as a machine learning model, continuously learning new classes without forgetting previous ones that it was trained on. So if you look on the diagram on the right, you will see you have one task where it learns 4 different classes, and then the model is trained, and then another task where 4 more classes are learned, and eventually this keeps happening until you end up with a model trained on all desired classes. The goal is to be able to learn new classes while maintaining good performance on all seen classes previously. So class incremental learning is essential for real-world applications, such as autonomous driving, many other adapting fields that involve large data sets. And so it's meant to mimic a lot like human learning, where you see new examples and can quickly learn. So some challenges that class incremental learning faces are, one is catastrophic forgetting. So this is the loss of those previously learned classes. So the way this happens is when the model's training, it updates weights for the new classes learned, and in turn, it will adjust them to negatively affect the ones that were previously learned. It also has a high computational complexity. So some motivation behind the project were to accelerate experimentation of class incremental learning utilizing A100 GPUs, which are found in the Tukey data science server here at UMass Dartmouth. And so the goal really is to accelerate class incremental learning research. So if things can happen faster, more models can be tested, more methods can be developed. So some objectives of the project were to assess A100 capabilities in class incremental learning, explore potential for accelerating experimentation. And then I did this by implementing the ResNet architecture with 2 different data sets. We used CyFAR100 and ImageNet. They are both image data sets. An example of CyFAR100 can be seen on the right. Those are 10 classes from CyFAR100. And so doing this, we apply 2 distinct incremental learning techniques, which I'll go over. And we optimize the A100 GPU configuration by distributing the training over 2 A100 GPUs. And we evaluate key performance metrics such as accuracy and training time. So the A100 GPU, as I mentioned, is part of the Tukey data science server. There's 2 of them. They both have 80 gigabytes of RAM. It is part of NVIDIA's Ampere architecture. It's designed specifically for AI data analytics and high performance computing. Some key features it has relevant to class incremental learning are tensor cores, which can help accelerate deep learning. And it also has a high memory bandwidth, allowing for information to go to and from the GPU very quickly. So the incremental learning methods I used, one was called GDUM, which is a simple memory efficient technique for class incremental learning. Its key features are that it stores a fixed number of examples per class and then trains on the stored examples without adaptation. Some advantages of this are it's an easy implementation and it has low memory requirements, but it has a potential for catastrophic forgetting. The other method I used was called ICARL, which stands for Incremental Classifier and Representation Learning, which learns a feature representation while updating the classifier. It also makes use of exemplars to represent each class. This allows for better class separation using those exemplars, and it addresses catastrophic forgetting. It is a more complex implementation. So the experimental setup I used were, again, the 2 incremental learning methods. I used 3 different GPU environments. So the first was Tesla T4 GPU in Google Colab. I used Google Colab Pro. And then I used a single A100 GPU in Tukey and then 2 A100 GPUs in parallel with Tukey. And so as you can see from the experimental matrix I have on the right, the ImageNet on both the T4 GPUs, even after adjusting the number of epochs to maybe make the training much less time, exceeded the 24-hour runtime of Google Colab, which I had purchased Google Colab Pro to eliminate that, but I guess that's not true. So the implementation is actually not too advanced because I began working from the original implementations of both GDUM and iCarl produced when their respective papers were published. They're both posted on GitHub. So I began by, I guess, working through that code and identifying which areas would need to be ran in parallel, as well as running the non-parallel experiments. I also needed to incorporate Sci-Fi 100 and the ImageNet datasets with them so that they could work with those, because ImageNet didn't come out of the box with either of them. I also integrated the distribution using PyTorch, and this was all done in Python. So I initialized the distributed environment within the training script. I wrapped the model with a distributed data parallel. This automatically splits the model and sends it to 2 different GPUs, and it handles gradient synchronization so that the GPUs are communicating. And then for the distributed training setup, as I mentioned, 2 A100 GPUs in parallel, and the data parallelism handled with distributed sampler, also in PyTorch. So here's my results. I'm not going to list off every single result because just for time purposes, but I do want to take note of a few things. So the accuracies seem really low if you're looking at these results. And so especially when training with ResNet. And so the accuracies are low just because of the incremental learning techniques. In a sense, like in a real world application, using incremental learning, you would probably start with a pre-trained model on a set of data and then incrementally add classes. But since these are all trained on every class is trained incrementally, it affects the accuracy. These are also fairly close, a bit lower, but fairly close to their the reported accuracies in their respective papers. And so that's what I was trying to do, trying to mimic those results. So something to note that the average efficiency speed up from a Tesla T4 to the A100 was 2.36. This might actually be larger if it ran for over the 24-hour time. And then the speed up from a single A100 to 2 A100s was 1.26, which is also good. I just have some simple visualizations here that sort of illustrate those results. So as you can see on the left, we have 2 A100s. This is for Sci-Fi 100, and this is training time. So as you can see, the different GPU configurations, the 2 A100 was slower, faster in training, and the single A100 was even faster than the Tesla T4, and the Tesla T4 was obviously the slowest. And then I have a speed up on the ImageNet data set. So this is speed up over the previous configuration. So we have at the bottom, we have the Tesla T4, and then the single A100, and then the 2 A100s. And then finally, I just have an average accuracy visualization on the right, which does show that the 2 A100s were most accurate in both cases. I'm not sure if that's because they're distributed. I don't think so. There's definitely other factors that could have affected the training processes of other ones that could have slightly affected the accuracies, as they were all pretty close. Obviously, the Tesla T4 on ImageNet is much lower because it didn't get to finish training. So some key points. So A100s demonstrated their potential in accelerating class incremental learning experimentation with a significant reduction in training time, especially compared to a more conventional GPU like the Tesla T4, where a lot of people would be working with. It also has a lot of real-world applications, such as in healthcare, autonomous vehicle, robotics. As we can train faster and faster, those things can update more quickly and give more human-like responses. So some future research opportunities is further optimization of the A100 GPU configuration. I think you could definitely probably work with the different data loaders to avoid basically GPU starvation, where it's sort of waiting for more data. And then obviously you could definitely look into the other incremental learning techniques, since I only looked into 2 here. I just have some acknowledgements. My Professor Ming Shao for his guidance and helpful in the project, and then the University of Massachusetts Dartmouth for the Tukey data science server supplying the A100 GPUs, which were very helpful. Thank you, and I'll answer any questions.
Since Tukey's a shared resource, do you have any issues with like runtime capabilities where the With other people using it.
Yeah.
One of my questions. Yeah.
Yeah, so it's definitely something to consider. I didn't specifically look for that. I definitely checked before running experience. If there was a bunch of people running something, I would wait. But definitely there was a lot of times where another student, Brian Cornet, you guys might know, was running a very large Julia simulation or something over a lot of the CPU cores, which I think definitely could have affected the results.
Past 2 weeks, probably.
Yeah, and so it's definitely something to consider that Tukey could, but I think the alternative would be to partition resources to different users, which I think would not allow everyone to use Tukey to its full potential. So I guess it's just a trade-off.
Should we buy more GPUs?
I think, yeah, more GPUs could be helpful, but then you run into the problem, as I mentioned, is like data loading might become too slow when trying to send that amount of data to different GPUs.
Any other questions? Great, there's a little tidbit you threw in there about the tensor cores doing mixed precision matrix arithmetic.
Yeah.
Is that something the user code has to worry about, or does it just know like where to use what kinds of precision and what?
No, I believe that's done within the GPU, because I know tensor cores are a fairly recent innovation in GPU architecture. So I think that's done within the GPU. I don't think the user has to define that.
Okay.
I believe.
Okay.